Press your hands together right now. Feel that resistance. Feel your palms pushing against each other. Solid contact. Skin touching skin. Simple enough, right? But here's the thing. Your hands are not touching. They have never touched anything in your entire life. Not once, not ever. This is not philosophy. This is not wordplay. This is physics at its most fundamental level. I spent my career exploring the deepest mysteries of the universe, black holes, the Big Bang, the nature of time itself. But this particular truth about atoms never fails to astonish me. It challenges everything we think we understand about physical reality. Let me take you on a journey into the space between atoms, into the invisible realm where touching becomes impossible. Start with something simple. Your hand. It looks solid. It feels solid. You can knock on a table and hear the sound of contact. You can pick up a cup and feel its weight pressing against your fingers. But zoom in. Keep zooming. Past the skin cells, past the molecules, down to the atoms themselves. What do you find? Emptiness. Vast, overwhelming emptiness. An atom is almost entirely empty space. If the nucleus of an atom were the size of a marble sitting at center field in a football stadium, the electrons would be tiny gnats buzzing around in the parking lot outside. Everything in between? Nothing. Vacuum. Empty space. Think about that for a moment. The chair you are sitting on is mostly empty space. The floor beneath you is mostly empty space. Your own body is mostly empty space. We are all ghosts pretending to be solid. So here is the first mystery. If atoms are mostly empty space, why does anything feel solid at all? Why do you not fall through your chair right now? The answer begins with electrons, those tiny particles orbiting the nucleus. They are the key to this illusion of solidity. When you press your hand against a table, you are not pressing atoms against atoms. You are bringing electron clouds close to each other, and those electron clouds refuse to merge. But why? What stops them? This is where the story gets interesting. This is where quantum mechanics enters the picture. The rules that govern the subatomic realm are unlike anything in our everyday experience. In the quantum world, electrons are not tiny balls orbiting a nucleus like planets around the sun. That picture is wrong. Useful, but wrong. Electrons exist as probability clouds, fuzzy regions of space where the electron might be found. Not definitely is. Might be. The electron does not have a precise location until you measure it. Strange, yes, but experimentally verified thousands of times. Now, when two atoms approach each other, their electron clouds begin to overlap. And something remarkable happens. A fundamental law of quantum mechanics kicks in. A law that makes contact impossible. It is called the Pauli exclusion principle. Named after Wolfgang Pauli, one of the pioneers of quantum physics. And it states something deceptively simple. No two electrons can occupy the same quantum state at the same place at the same time. Read that again. No two electrons can be in the same state in the same location simultaneously. This sounds abstract. Let me make it concrete. When you push your hands together, the electrons in your left hand approach the electrons in your right hand. As they get closer, the exclusion principle creates resistance. The electrons cannot occupy the same space. They push back. That feeling of pressure, that sensation of solidity, it is not atoms touching. It is quantum mechanics preventing overlap. It is the exclusion principle saying no. Here is the truth that should disturb you. There is always a gap. Always. No matter how hard you push, no matter how much force you apply, the electron clouds never truly merge. They get close. Incredibly close. But they never touch. Your hands have never touched each other. You have never touched another person. Every kiss, every handshake, every embrace, all separated by a quantum gap. The sensation of touch is real, but actual contact, that is an illusion created by electromagnetic forces and quantum rules. Now things get strange. Because I have only told you half the story. The exclusion principle explains why electrons resist each other. But there is another force at play, a force that makes this even more fascinating. The force I am referring to is electromagnetism, one of the four fundamental forces of nature, and it plays a crucial role in this illusion we call touching. Let me explain how it works. Electrons carry negative charge. Every electron in the universe has the same negative charge. This is a fundamental property like mass or spin. Now, here is a basic rule of electricity. Like charges repel, opposite charges attract. Two positive charges push each other away. Two negative charges do the same. Think about that for a moment. When your hand approaches a table, billions upon billions of electrons come near each other. Negative meeting negative, repulsion meeting repulsion. Before the electron clouds even get close enough for the Pauli exclusion principle to matter, electromagnetic repulsion is already pushing back. The negative charges in your hand are being shoved away by the negative charges in the table. This happens at a distance, no contact required. Imagine two magnets with the same poles facing each other. You can feel the resistance before they meet. Push harder, the resistance increases, but they never actually touch. There is always that invisible cushion of force between them. Same pattern, same physics, just at a much smaller scale. Your entire experience of solidity is electromagnetic repulsion. Every surface you have ever felt, every object you have ever held, all of it is electrons pushing electrons away through empty space. The atoms never meet, the electrons never collide. Forces bridge the gap instead. Here is an analogy that might help. Imagine two boats on a lake, each creating waves. As the boats approach each other, their waves interact. The boats slow down, pushed apart by the rippling water between them. They never need to collide. The waves themselves create resistance. Electrons are similar. They do not need to crash into each other. Their fields interact. Their charges create forces, and those forces feel exactly like contact to our human senses. But there is no contact, only forces acting across empty space. Now let me address something you might be wondering. If atoms never actually make contact, how does anything stick together? How do molecules form? How does chemistry work? This is a beautiful question, and the answer reveals even more about the quantum nature of reality. When atoms bond, they do not collide and stick. Instead, they share electrons, or they transfer electrons from one to another. The electron clouds overlap partially, creating a lower energy state, a more stable configuration. Think of it like two people holding hands. They are not merging into one person. They are sharing space, connecting through interaction, not fusion. Chemical bonds are electromagnetic relationships, attractions balanced by repulsions, electrons dancing between nuclei, holding atoms in fixed arrangements. But even in the strongest chemical bond, the nuclei of the atoms never come close to meeting. They remain separated by relatively enormous distances. The bond exists in the electron cloud, not in atomic collision. Here is the thing. We use the phrase atoms bonding as if atoms were snapping together like Lego blocks. That image is completely wrong. Atoms bond through fields and forces and quantum mechanical sharing, never through contact. The same applies to everything you consider solid: steel, diamond, bone, all held together by electromagnetic forces across quantum gaps. Let me give you some numbers to appreciate the scale. The typical distance between bonded atoms is about 1 angstrom. That is 1/10,000,000,000th of a meter, incredibly small by human standards. But the nucleus of an atom is about 100,000 times smaller than the atom itself. So even when atoms are bonded, their nuclei are like two cities separated by an ocean. The electron clouds touch in the sense of overlapping, but the atoms themselves, never. The nuclei remain isolated islands surrounded by seas of probability. Stop and think about what this means. Every solid object is a conspiracy of forces, a collective illusion maintained by electromagnetic repulsion and quantum exclusion. The sensation of hardness is real. The solidity is not. You have walked on floors your entire life, but you have never truly stood on anything. You hover above surfaces, suspended by invisible forces, separated from the ground by quantum mechanics. This is not poetry. This is measured, verified, experimental truth. Now I want to take you deeper, because the story becomes even stranger when we examine what happens at extreme scales. What occurs when you push atoms closer and closer together? What breaks first, the atoms or the rules? Let me take you to the extremes of pressure and density, places where atoms are forced closer together than anywhere on Earth, places where the quantum rules I described face their ultimate test. Start with something familiar, water. Put water under pressure and it resists. The molecules push back, increase the pressure further, and eventually the water compresses slightly. But there is a limit. Push too hard and the molecular structure breaks down. The chemistry changes, but the atoms themselves, they still refuse to merge. Even under enormous pressure, electron clouds maintain their distance. The Pauli exclusion principle holds firm. Now consider something more extreme, the core of our planet. At the center of Earth, pressures reach over 300 billion pascals. Temperatures exceed 5,000 degrees. Iron atoms are squeezed together with tremendous force. Yet those iron atoms never touch. The electron clouds resist. The electromagnetic repulsion persists. The core is incredibly dense, yes, but the atoms remain separated. Forces bridge the gaps as they always do. Here is the thing. To truly force atoms closer, you need pressures far beyond anything Earth can produce. You need the crushing gravity of a dying star. Think about that for a moment. When a massive star exhausts its nuclear fuel, gravity wins. The outer layers collapse inward at tremendous speed. The core is crushed under unimaginable pressure. What happens to the atoms? Initially, they resist. Electron clouds push back with all the force quantum mechanics allows. This resistance is called electron degeneracy pressure. It is the Pauli exclusion principle working at cosmic scales. For smaller stars, this resistance wins. The collapse stops. The star becomes a white dwarf, an object where atoms are packed incredibly tight but still maintain their quantum separation. A teaspoon of white dwarf material would weigh several tons on Earth, yet even there, atoms do not truly touch. They are simply squeezed as close as quantum mechanics allows. But for larger stars, something different happens, something remarkable and terrifying. If the collapsing core exceeds about 1.4 solar masses, electron degeneracy pressure fails. The electrons cannot resist anymore. Gravity overwhelms them. What happens next defies everyday intuition. The electrons are forced to combine with protons. They merge into neutrons. The atom itself ceases to exist in any recognizable form. Protons and electrons become one. This is a neutron star, an object where atomic structure has collapsed entirely, where matter has been compressed beyond the point where our normal concepts apply. A neutron star packs the mass of our sun into a sphere roughly 20 kilometers across. A teaspoon would weigh billions of tons. Stop and think about what this means. The Pauli exclusion principle does not fail. Instead, the particles change identity. Electrons and protons become neutrons, and neutrons have their own exclusion principle, their own resistance to compression. Neutron degeneracy pressure now holds against gravity. The neutrons refuse to occupy the same quantum state. They push back. But even this has limits. For the most massive stellar cores, even neutron degeneracy fails. Gravity overwhelms everything. The matter falls inward forever. This is a black hole, a point of no return, a place where our physics breaks down entirely. Here is the beautiful part. The same quantum rule that prevents your hands from truly touching also determines whether dead stars become white dwarfs, neutron stars, or black holes. The Pauli exclusion principle shapes the ultimate fate of matter in the universe. Same pattern, same physics. From your fingertips to dying stars. Now let me connect this to something even more fundamental. The reason electrons obey the exclusion principle relates to their quantum identity. Electrons are what physicists call fermions, particles with half-integer spin. All fermions obey the exclusion principle. Electrons, protons, neutrons, quarks, they all refuse to share quantum states. But not all particles are fermions. Some are bosons, particles with integer spin, photons, gluons, the Higgs boson. Bosons follow different rules. They can occupy the same quantum state. They can pile on top of each other without limit. This distinction, Fermion versus boson, determines the fundamental behavior of matter. It explains why atoms have structure, why chemistry works, why you cannot walk through walls. The universe has two categories of particles. One refuses to share. One shares freely. And this refusal to share, this quantum stubbornness of fermions, is why nothing ever truly touches. Let me bring this journey to its conclusion. Let me show you what this all means for your existence, for reality itself. We began with a simple observation. Your hands pressing together. The feeling of contact. The sensation of solid meeting solid. Now you understand the truth beneath that sensation. There is no contact. There never was. Electromagnetic forces push back across empty space. Electron clouds refuse to merge. The Pauli exclusion principle forbids overlap. Quantum mechanics creates the illusion of solidity from fundamental emptiness. Think about that for a moment. Every object you have ever held was held at a distance. Every surface you have ever walked on was a quantum hover. Every person you have ever embraced was separated from you by forces invisible and absolute. This sounds isolating, it sounds cold, but here is the thing, it is actually beautiful. The forces that prevent contact are the same forces that give matter its structure. Without electromagnetic repulsion, atoms would collapse. Without the exclusion principle, electrons would fall into the nucleus. Matter as we know it would cease to exist. The very rules that keep you from truly touching something are the rules that allow you to exist at all. Same pattern, same physics. Separation enables existence. Let me take this further. Every atom in your body was forged in the heart of ancient stars. Hydrogen fused into helium, helium into carbon, carbon into oxygen, on and on through the periodic table. Those atoms traveled across space for billions of years. They assembled into planets, into oceans, into living cells, into you. And throughout that entire journey, those atoms never once touched another atom. They interacted through forces. They bonded through electron sharing. They assembled into complex structures through electromagnetic relationships. But contact? Never, not once in billions of years. You are made of particles that have never truly met. Your existence is a collaboration of strangers communicating across quantum gaps. Stop and think about what this means. The universe is not a collection of solid objects bumping into each other. It is a web of relationships, a network of forces, a dance of fields interacting across empty space. Matter is mostly emptiness held in shape by invisible rules. Here is another perspective that might shift your understanding. When you look at a table, you see a solid object, but a physicist sees something different. A physicist sees a region of space where certain forces are concentrated, where electromagnetic fields create resistance, where quantum rules define boundaries. The table is real, its effects are real, but its solidity is an emergent property, a result of deeper laws working at scales too small to see. This applies to everything. Your body, the earth, the stars, all of it is forces and fields and quantum mechanical relationships. All of it is interaction without contact, connection without collision. Now let me leave you with one final thought. I have spent my life studying the universe at its most extreme. Black holes where space-time itself breaks down, the Big Bang where everything began from almost nothing, the quantum realm where particles exist in multiple states simultaneously. But this simple fact about atoms never touching contains the same depth, the same strangeness, the same beauty. Reality is not what it appears to be. The solid world is an illusion built from emptiness and force. The sensation of touch is real, but actual contact is forbidden by the fundamental laws of physics. You have never touched anything, you never will, and neither has anything else in the entire universe. Every interaction in cosmic history has occurred across a gap. Every force has bridged empty space. Every relationship between particles has been mediated by fields, not contact. The universe is connected through separation, united through distance, whole through emptiness. That is the beautiful part. We search for connection. We reach out to touch each other and the world around us. And though we can never truly make contact, the forces between us are real. The interactions are genuine. The relationships matter. You are not isolated by this quantum gap. You are participating in the same physics that governs stars and atoms and everything between. Your existence is proof that emptiness can create structure, that forces can substitute for contact, that connection does not require collision. The atoms in your body have never touched, yet here you are, thinking, wondering, existing. That is not a limitation, that is a miracle.